Hello everyone. This is lecture 5 of module 2 and I'm your guide Akanksha Singh who will be taking you through the entire series of lectures that are associated with network security and cryptography. We've already gone through a lot of topics in lecture 1, 2, 3, 4, and my recommendation is again that please go through all my videos that are made previously to understand this lecture. Okay, so moving ahead to today's lecture, we'll be studying about various primality tests. What do you mean by prime numbers? I've already talked about it, and today we'll be discussing about primality test. Okay, so let's move ahead to understanding test for primality. Now, there are many cryptographic algorithms. Okay, so there are many cryptographic algorithms that are available for finding out which number or for selecting which number is a prime number. What do you mean by testing for primality? Let me first tell you. Testing for primality is actually testing whether a number is a prime or not. Whether a number is prime or not. This is what I mean by primality testing. Right now, there would be a question in your mind as to why do we need this? We can easily tell whether a number is a prime or not, right? For 7, it is very easy to tell whether it is a prime number or not because you just have to see whether the number is divisible by any other number apart from 1 or itself. Since 7 is not divisible by any other number apart from 1 and itself, it is a prime number. Okay, now up till numbers of digit, it is easy. It is easier for you to tell whether a number is prime or not. But for a numbers that are in large, right? Large numbers, maybe 2 to the power 1000, maybe 561 to the power 1000. Now, if the number is so large, for that number, if someone asks you whether this number is prime or not, it becomes very difficult, right? And probably there are no confirming test that would tell you that this number is a prime number, surely prime number, if the number is very big. So and we are going to study in future. There will be various algorithms which will be telling you to choose large enough prime numbers. Now, how do you choose a large enough prime number when you cannot decide whether a number is prime or not, right? So there are various tests, and I'll be teaching you today the probabilistic test for guessing whether a number is prime or not. Basically, if the probabilistic test is not used, what we do is we make a sample space of random numbers, large sample space of random prime numbers that are for sure prime number. Such sample spaces are already made, and from those sample spaces you can pick up the large prime numbers. But if you do not want to pick up the numbers from the sample space and you want to have other numbers and you want to make it sure whether it is a prime number or not, there are probabilistic tests for deciding whether a number is prime or not. So if you do not want to use probabilistic test, there are already available random spaces for prime numbers, sample space, that is, some huge numbers are already made sure that these are prime numbers and that they are already published. So from those numbers you can choose one of the large prime numbers. But today I'll be teaching you the probabilistic test, which will be making you, or which will be guiding you to decide whether a number is prime or not. Okay, so coming to probabilistic test. Now, what is probabilistic test? Now, many popular primality tests are probabilistic. these tests use, apart from tested numbers n, some other numbers which are randomly chosen from the numbers that are available. Okay, so let's start. There are two probabilistic tests that we'll be studying. The first one is the Fermat's primality test, and the second one that we are going to study is Miller Rabin test. Okay, so please focus on what I'm saying. It will be easy for you when you listen to me. Okay, so Fermat's primality test. Now, Fermat's primality test is based on Fermat's theorem. I hope you remember Fermat's theorem. Fermat's theorem was, right, a to the power p minus 1 congruent to 1 mod p. That is Fermat's theorem, where p is a prime number and a and p both are relatively prime. If you remember this, GCD of a and p is relatively is equal to 1. Therefore, you can say that they are relatively prime. I've already taught you this in lecture number 3. Okay, so we'll be using this theorem for probabilistic test of prime numbers. Okay, now how we'll be using this theorem? Let's start. For example, you want to test if n is a prime number or not, right? If n is a number that is given to you and you want to know whether this is prime number or not. Okay, what will you do? Okay, let me start by the first step. Choose integer a, right? You have to choose an integer a less than n. Remember, it should be less than n. For example, if the number that you have to decide whether it is prime or not is 56, then you have to choose a such that it is lesser than n and greater than 1. Okay. Okay, so I hope you have understood that. So the minimum value that you can choose is 2. Okay, and maximum is just lesser than the number that you have to decide whether it is a prime number or not. Okay, so moving ahead, after choosing a, what you will do is then you will compute a to the power n minus 1 mod n. A to the power n minus 1 mod n. After computing this, now let me make it more specific. You will be computing this. Okay, after computing this, if a to the power n minus 1 is congruent to 1 mod n, if your value that you've chosen for a is such that when you write the value of a here and when you write your number that you have to decide whether it is prime or not here, such that a to the power n minus 1, if it is not congruent to 1 mod n, if it is not congruent to 1 mod n, then you can be very sure that that number is a composite number. For sure it is a composite number. Now there could be a doubt in your mind as to what composite numbers are. See, composite numbers are those numbers that are not prime numbers. To be more specific, composite numbers are those numbers that can be divided by itself, by 1, and by one more number apart from 1 and itself. Okay, those numbers are called as composite numbers. So when a to the power n minus 1 is not congruent to 1 mod n, then that number is a composite number. If a to the power n minus 1 is congruent to 1 mod n, then probably you can say that it is probably a prime number, right? Here also remember, it is not a short test that since a to the power n minus 1 is congruent to 1 mod n, it is going to be a prime number. No, it can be probably a prime number, right? I'll also tell you something more, a very interesting fact about it. If a to the power n minus 1 is congruent to 1 mod n, right? If a to the power n minus 1 is congruent to 1 mod n and still n is not prime, I said here in this condition, I told you that if this condition is true, then n is probably prime. But what if it is not prime? if it is not prime, then it is called as pseudo prime number. Why is it called as pseudo prime number? Because it looks like a prime number, but it is not a prime number. Okay, so numbers that are congruent to a to the power n minus 1, congruent to 1 mod n, and n still is not prime, then such numbers are called as pseudo prime numbers, or are called as Carmichael numbers. Carmichael numbers, Carmichael, Carmichael numbers. Okay, so such numbers are called as Carmichael numbers, wherein when you find out a to the power n minus 1 and it is congruent to 1 mod n, and in this situation n is not prime. If n is not prime, then that number is called as Carmichael number. Okay, now, okay, for up till what a you will be testing for n, up till what age you will be testing for n whether that number is prime or not. Test for all a between 1 to n minus 1, that is from 2 to n minus 2. Okay, I hope you can understand. Okay, let me pick up an example to illustrate this entire procedure. I have written an example here in the short form. Okay, I hope it is not messy. Okay, let me start. My question is 23 a prime number? Okay, my question starts whether the 23 is prime number or not. Now, what can we do? Okay, for n is equal to 23, because if I have to decide whether a number is prime or not, I will say n is equal to 23, and then I will start choosing a. Now, how can you choose a? You can choose a from 2 to 21, right? Less than n minus 1. Here, if you can see, less than a should be less than n minus 1. Less than n minus 1, n is what? N is 23. 23 minus 1 is 22, and it is not equal to. I have not written equal to here. As you can see, it is just less than, so it should be 21. So up till 21 you can pick up a, and you can start from a as 2. Okay, so choose a is equal to 2. We have chosen a is equal to 2 and written that in the form of Fermat's theorem, a to the power 23 minus 1, which is 22, congruent to 1 mod 23. Is that true? Is this true? Yes, this is true, right? Since this is true, hence we can say 23 is probably prime, right? See, the Fermat's primality test does not tell you whether it is short a prime number or not. Okay, moving ahead, choose a is equal to 3 and then test whether this is equal to 1 mod 23. If this is true, then it is more certain that this is a prime number. If you keep on doing it, and if you do it till n minus 1, that is till 21, and you make it sure that it is going to be congruent to 1 mod 23 in all these situations, then you can say that it is a prime number. Okay, so this is Fermat's primality test. I hope you have got it. Fermat's primality test is based on Fermat's theorem, right? And if you have to decide whether a number is prime or not, you have to choose integers a such that they are greater than 1 and lesser than n minus 1, and then start computing that with for a is equal to n minus 1 is congruent to 1 mod n or not. If it is congruent to 1 mod n, then you probably are reaching to prime number, and if it is not congruent to 1 mod n, then it is short a composite number. Okay, and if this is true and still n is not prime, you can call n as pseudo prime numbers or Carmichael numbers. Okay, so moving ahead to my second test, which is Miller-Rabin test. Miller-Rabin test. Okay, now I'll be discussing what Miller-Rabin test is. Now, Miller-Rabin test is basically based on the basic principle, which says x to the power 2 is congruent to y to the power 2 mod n. If you remember, I told you the properties of congruency, wherein I told you x to the power 2 is congruent to y to the power 2 mod n. But in this situation, x should not be congruent to y mod n. Okay, so if this is the condition, if this is the condition that x is not congruent to y mod n, then you can say n is a composite number. Okay, this is the principle that we're going to use. This is the principle that we're going to use. Okay, so we've already studied this principle in congruency. Please go to my lecture number 3 and understand the congruency properties to understand this principle. Okay, so we'll be moving ahead to understanding algo of Miller-Rabin test. Okay, so see the algo. I'll first illustrate the algo and then perform a numerical, maybe two numericals, to make you understand what this algorithm is saying. See here, first I have to find out n minus 1 is equal to 2 to the power km, such that k is the largest value that satisfies this condition. Okay, k should be the largest value that satisfies this condition. After this, after finding out this, choose a. How you have to choose a? You have to choose a between 1 to n minus 1, and then moving ahead to compute b naught is equal to a to the power m mod n. Here, if b naught is equal to plus 1 or minus 1, then you can say n may be prime, then n is maybe a prime number. But if b is not equal to plus 1 or minus 1, then further go on to finding b1, which is equal to b naught to the square mod n. Now if the result is plus 1, then you can surely say that this is a composite number. Okay, else if the result is minus 1, then you can say that it is maybe a prime number. Again, if b1 is neither equal to plus 1 or minus 1, then keep repeating the procedure, this procedure. Step number 4 will be repeated if you do not find bi equal to plus 1 or minus 1. You can keep repeating this procedure. Okay, so let me take up an example to make you understand what Miller-Rabin test is. Okay, so let me pick up an example. Okay, 53. My question is 53 a prime number? Is 53 prime? This is the question. Okay, now what am I supposed to do? Initially I'm supposed to find out n minus 1 is equal to 2 to the power km. This is what I know, and here I know that my n is equal to 53. So basically 52 is equal to 2 to the power k dot m. Okay, now I'm supposed to choose k such that k, the value of k is largest. How will I choose that? 52 upon 2 to the power k is equal to m. That is what I have derived from this equation. Now I have to choose k, the largest k. Okay, so start choosing 2 to the 52, 2 to the power basically 2 to the power 1. Start from 2 to the power 1. This will give me m as 26. Okay, moving ahead to choosing other value of k, which is 2 to the power 2, which gives me m as 13. Okay, then move ahead for choosing k as 3, which will give me m as 65. Okay, now what am I supposed to do? I told you I have to choose k such that it helps me in finding out the largest value of m, which is just this which is smaller than n, largest value of m which is smaller than m. Okay, so 26 is smaller than n. 26 is smaller than 53. 33 13 is smaller than 53, but 65 is not. So basically my k, the largest k, basically my largest k is now going to be 2. Okay, so I'm going to choose my k as 2 and my m value as 13. I hope you got to know how to choose the value of k and m. What you have to do is you have to perform, you have to keep repeating the k, the value of k. such that the value of m is smaller than 53 and not larger than 53. Okay, for 26 it was still smaller, the value of k was okay. For the 13 the value of k was okay, but for 65 m was large enough, larger than 53. Therefore this value was not acceptable, so the largest value of k was 2, for which the value is still lesser than 53. So the k is 2 and m is 13. Now let us choose the value of let's choose it as 2, since we know that this is the we have to choose a value from between 1 to n minus 1. I'll be choosing a as 2. After choosing a as 2, find out b naught. B naught is equal to a to the power m, as you can see from here, a to the power m mod n. Now what is the value of a? A is 2, and what is the value of m? M is 13, and for n we have taken n as 53, right? So 2 to the power 13 mod 53. The value of 2 to the power 13 mod 53 is if you calculate this by calculator, you get that this is neither equal to plus 1, neither equal to minus 1, right? So the value is neither equal to plus 1, neither equal to minus 1. So we'll be further moving ahead to finding out the second step. As you can see here, if you do not get plus 1 or minus 1, if you do not get this, then find b1 is equal to b naught. Now what was the value of b naught? Okay, it was very important for finding out what was the value of b naught. If you calculate this by calculator, you'll get that the value of b naught is 30. So 30, so b naught ka square is what you have to find out, mod n. So b1 is going to be equal to 30 square mod 53, right? So after finding out this, you will find out that your b1 is equal to minus 1, right? Your b1 is equal to minus 1 if you calculate this. Now if you calculate this, see, do not get confused, I've already told you the exponentiations calculation, right? The bigger number calculations. So I'm just moving directly to the calculations, that this is 30. I have already discussed it this in lecture number 4, modular exponentiation, so I'm not skipping the part. Okay, so if here, since I have calculated that b1 is equal to minus 1, see here, if your b1 is equal to minus 1, you can probably say that your number is prime. So here probably the number is prime, that is your answer. You can say that probably the prime number is the 53 is prime number by Miller-Rabin test. Okay, so this was the whole explanation about Miller-Rabin test. My next topic is Chinese remainder theorem. This is the next topic of this lecture, Chinese remainder theorem. Now, Chinese remainder theorem. What does Chinese remainder theorem states? Chinese remainder theorem says that if there are numbers n1, n2, n up till nk, which are relatively prime, and if you pick up them, pick up these numbers n1, n2, nk up till nk pairwise, and those pairwise numbers are relatively prime integers, and if there are numbers a1, a2 up till ak, then there exists a unique integer x that satisfies all the congruent equations such that this is true. Okay, let me explain what is written. See, basically I am trying to tell you that if these are prime numbers n1, n2 up till nt, right? There can be many equations here. So n1, n2 up till nt are prime numbers, and these are pairwise. What? These are pairwise relatively prime. n1, n2 is prime, maybe n3, n4 is prime, maybe n5, n6 is prime. Okay, so these are pairwise prime. Okay, and there are integers a1, a2, positive integers a1, a2, at up till at, such that there is a congruent number. There is a number which is equivalent to all these equations. There's a unique integer which satisfies all these equations. Okay, that is the Chinese remainder theorem. Chinese remainder theorem states that there is going to exist a unique integer that satisfies all these congruent equations such that a1, a2, a3 up till an are the positive integers, and n1, n2, n3 up till nt are pairwise relatively prime integers. Okay, so this is what is Chinese remainder theorem. Now, here this x is equivalent to n1 x1 a1 plus n2 x2 a2 plus up till nt xt at, where ni is equal to capital N upon ni. Okay, this is the entire Chinese remainder theorem that you have to remember. You have to remember what Chinese remainder theorem says. Chinese remainder theorem states that there is a unique integer x such that it satisfies multiple congruent equations wherein the n is a prime number and is relatively prime to pairwise prime numbers, and there are positive integers a1 a2 up till at. Not only positive integers, there can be negative integers too. Okay, so let's move on to understand this Chinese remainder theorem with the help of an example. Okay, I'm going to pick up an example and explain you what Chinese remainder theorem is. Question is, okay, so let's see the question. The question is, there are these three congruent equations and you have to find out what is the value of z. Okay, so by the theorem, as you can see here, by the theorem I told you that x here, there was a unique integer x, and here in the question they are saying that find out z, which is unique integer for all these congruencies. So basically the formula is n1 x1 a1 n2 x2 a2 n3 x3 a3. Okay, so from the above equations I got to note that my a1 a2 a3 are these values 3 1 4. So I know that my a1 is 3, I know that my a2 is 1, and I know that my a3 is 4. Okay, this is what I know. This is all I know. Now for finding out n, what is capital N? The capital N, the value of capital N is equal to small n1 into n2 into n3. Now what is that? N1 is 8, n2 is 9, n3 is 11. Now 8 into 9 into 11, 8 into 9 into 11 will give you value, if you multiply, and you'll get as 792. Now 792, now we are supposed to find out n1, capital N1, and we've just found out what n is. So how to find out capital N1? From this formula you can derive what n1 is. The capital N is 792, and for first n1, the small n1 is going to be 8. So your capital N1 is now going to be 99, right? Similarly, if you find out N2, 792 divided by 9, it is going to give you 88. And similarly, N3 is going to give you 792 divided by 11, which is, the value is 72. Okay, so this is 99, 88 and 72 are the values for capital N1, N2 and N3. Therefore, by far what all values we've got the value of 99. We do not know what x1 is. We got 3, plus we've got 88. We do not know what the value of x is. We've got what 1 is, plus the value 72 into, we have to do some value x1, and we do not know the value, and we know what is 4. Okay, so till here we know this. Now according to Chinese remainder theorem, n1 and x1 is congruent to 1 mod n1, right? We know this. So n1 is 99 and x1 I do not know, and 1 mod small n1 is 88. This is what I know. Since this is what I know, what I can do is, how can you find out the value of x1? It is very simple. The value of x1 here will be, here can be 3. Okay, so you'll be confused how to find out how I've calculated x1 is equal to 3. Now there's a small trick for finding out this. Whenever you have this equation, always try to find out the this is just 8, I'm sorry, this is just 8, right? N1 is 8, only 8, I'm sorry. Okay, so always try to find, if this is the equation and you are supposed to find out x1, how you can do, you can just find out the factors of 8. You can just find out the factors of 8. So keep finding out the factors of 8 which is just smaller than 99, which is just smaller than 99. So which factor is just smaller than 99? 96. If you if you count a table of 8, you will be getting 96, which is just smaller than 99. After that is a bigger value than 99. So when I got the factor, what am I supposed to do? Just do 99 minus 96, which you get as 3, and that is the answer. 3x1 is equal to 1 mod 8. Okay, now if you have a confusion, please remember what I told you in congruency. In congruency, I told you mod 8 is a circular arithmetic, which is from 0 to 7, right? From 0 to 7. That is, every time 7 comes, the congruent value is going to be same. That is the concept. So basically what I'm doing, I'm actually trying to find out the factors of 8. All the factors of 8 is going to be actually the complete cycle. The cycle is going to be completed at that factor. So basically I decided that after that, just let me find out the factor which is just lesser than 99, because I know for that factor the value is 0. For 96, for 8, 16, for all these numbers, the factor is the answer, the congruent value is going to be 0, right? So similarly, for 96 also the congruent value is going to be 0. So what I decided is just perform 99 minus 96, only that has to be calculated. So 3x1 is equal to 1 mod 8, right? Now it is going to be easier for you to calculate what x1 is, isn't it? Now you can say that your x1 is 3. So similarly, you can go ahead and find out what is the value of x2 by writing down the equation n1 x1 is congruent to 1 mod n1. You will get that your value of x2 is minus 5, and your value of x3 is going to be equal to 2, right? So after doing this, please calculate your z value, that is 99 into 3 into 3 plus 88 into 5 into minus 5 into 1 plus 72 into 2 into 4. For that you get z as, if you calculate, you get z as 1027, right? After calculating z, you get 1027. Now there's one more very important thing that I would like to tell you, is that the answer for Chinese remainder theorem can be various. It is not necessary that the answer is going to be just one. Why? Because it is not necessary that the congruency is always going to be 3. You can also find out other congruencies also, right? You can find out multiple congruencies. Why? Because the value or the cycle of the congruent cycle of the modular arithmetic keeps repeating. Okay, so I hope you have got the entire concept. So thank you, class, for today. This is all. We'll be moving ahead for next lecture, that is lecture number 6, and we'll be discussing about what is RSA, Rivas Shamir Eldemer technique, in the next lecture. Thank you so much.